question about what are the technical challenges of LTE to become the leading technology also in machine-to-machine communications? Please, Christian, at your time.
Thank you, Owen. So M2M is a very exciting field today to be in. We're seeing the first massive deployments of machine-to-machine communications in smart metering, other applications. But interestingly, a lot of this is happening outside the cellular world. Other technologies are being used, such as power line communications or extensive mesh deployments over unlicensed bands. So I have somehow the feeling that these efforts could be short-lived if LTE is able to respond to these machine terminal needs in the right way. Because I can't think of a more cost-effective way to serve end-to-end than using existing cellular infrastructure, base stations over privileged positions, being able to aggregate traffic from a very high number of devices with very low traffic needs. So I'm going to argue for the need of some technological changes over the current design of LTE. First, it is clear that M2M represents a very large growth opportunity for LTE. One first step is that LTE should be able to eventually replace 2G solutions that are leading the market today, interestingly. Now, the reason it is not doing that is mainly cost. And that is because LTE was designed for human data communications. It was designed to respond to the capacity crunch. Very high terminals with very high data needs, very advanced terminals. Now the LTE end-to-end solution is going to be based on new technical solutions. It will also require new business models, which I'm not going to talk about, but it is a fact. And it is going to compete and complement with other existing technologies, such as wireless sensor networks, satellite, or other wide area network standards. So as I'm illustrating here, in end-to-end systems, the network sits right in the middle of it. Getting the right network to communicate machines is the most important part of it. So the technical challenges that M2M is presenting to LTE are many. First of all, we have very heterogeneous application requirements. You can't define the requirements for all M2M applications. You can define them for one. But you have, for example, applications that are delay tolerant, applications that are delay critical, for example, e-health. Terminal capabilities are also very heterogeneous. Some terminals can be very expensive. Some other terminals are going to have to be really cheap if the application is going to be deployed. Coverage is also an issue. We all know that coverage is still a problem. Our solution when we don't have coverage is to just move to another place where we have coverage. But machine terminals are not going to be able to do that. So we really need to improve coverage. Energy constraints are, again, very important. These terminals are going to be deployed in large numbers. We don't want to go and service them very often because it's going to be very expensive. So we want them to live as long as possible on their batteries. Store messages are going to be the kind of traffic predominant in many M2M systems. And high scalability is also going to be an issue. We're going to have millions of terminals registered, perhaps to every base station, a very large number. And finally, security is also important for, you can imagine, a lot of critical applications where you don't want the system to go down. Regarding all this, we are working in the FEMTO project of the European Commission with the major operators and service providers and application designers to try to define new technology solutions for LTE to service the M2M market. And the main lines of our solutions are first, segmentation of M2M services. For high-end M2M services, we believe LTE technology as it is very good. It's very bandwidth, it's very spectrum efficient, and it's very well designed. On the other hand, for low-end M2M services and terminals, we need new technologies to reduce the cost very significantly. More on the server and network side, this device, we need very robust device management protocols that we know that are going to not fail, and we want them to be secure. So we need distributed security algorithms to all these terminals. More regarding what's the air interface, we need to optimize the system for small packet access. Think of packets that could be 10 bits long. If you, for example, have a switch on and off signal with the added security and so on, 10 bits long or maybe 100 bits long. We need to find a good, it is not efficient to set up a channel for such a short communication. It is probably more efficient to use a random access over the data channel to transmit the data itself, not to access to the channel. We also need to develop hybrid RQ mechanisms, collective acknowledgements, all the things that ensure that our device can be turned off most of the time. Another point that we need to improve on is coverage of the network. We want all the corners in the city to be covered, even basements where the smart meters are sitting or places where you wouldn't think of making a phone call. So we need improving budget. We probably need lower modulation and coding rates that are increase the link budget. We're going to have to need relaying and capillary extensions of this network. Probably it is going to be impossible to reach all the destinations from the base station. And that's going to imply a major physical layer redesign if you really want to bring the cost down to the appropriate level. Finally, energy efficiency is very important because the cost of the terminal not only comes from the chipset, but it also comes from what it needs to have to keep it running. So we want the smallest battery possible. We want it to have the longest lifetime possible. So we need to be very aggressive on the duty cycle. These devices need to be off 99.9% of the time as possible or more. And we need to adapt the network to that. We need to reduce signaling. We need to come up with efficient access mechanisms. We also need to reduce the bandwidth. There is no need for a machine terminal that turns on a traffic light, for example, or a street light to have a 20 megahertz bandwidth, and that's obviously very costly. Signaling for mobility is again an issue. These terminals many of them are not going to be very mobile, so we shouldn't. So the current paging system may not be appropriate. Energy harvesting is a promising solution to keep the terminals running longer. So a lot of these terminals are going to be able to harvest energy from the environment through solar panels or vibration harvesting devices, even electromagnetic harvesting. So we need to make sure that what we design can live with such an unpredictable energy source. And finally, offloading to the local network is also a solution in terms of efficiency because it allows you to communicate to shorter distances. So with all this input and with all these ideas, the Exalted project is coming up with an architecture that's reshaping of LTE appropriate for the M2M services, which we call LTE-M. And it is basically going to consist of the existing LTE infrastructure and probably a redesign of some aspects of its physical layer, of its control plane, but still with the idea of reusing as much as possible the very expensive infrastructure that is already there. This architecture is going to consist of the cellular deployment, and it's going to be complemented with what we call capillary extensions, which are going to be gateways that service local area networks or smaller mesh networks. These mesh networks could still use the license band, but we want to extend the relaying capability of LTE for the sake of coverage. So these are the main ideas that we are working on, and some solutions are coming out in in terms of new technologies for the air interface and new solutions for signaling and other issues.
Thank you very much, Christian.
Visit cttc.es for more information.